Hello everyone, how are you? Welcome back to your favorite channel. This is Met Zone African Motives. So we are back at it again. Now we are now revising and preparing for our November examinations. So today I brought you a question paper which was from the Eastern Cape Province, and it was for grade 11. It was written in November 2024. It was a physical sciences paper 2 question paper, which is usually chemistry. And the question paper was out of 150 marks, and it was supposed to be written in 3 hours. So let's use this question paper to revise and prepare for our final exams. So the question paper is into two sections. The first section is multiple choice, and then the second question it's open-ended questions. So on multiple choice, as usual, you would be given four choices to choose from, which is four options, which is either option A, B, C, or D. And there is always only one correct answer, which is more accurate. So we need to choose wisely. So let's get started and see how the question paper was made of. So on question number one, which is 1.1, they were saying, which one of the following bonds will have the highest bond energy? So here we are given a single bond, a double bond, and a triple bond. And we know that a triple bond is more stronger than a double bond as well as a single bond. So the one to have the highest bond energy is the strongest. So our answer, our option there was going to be D. So the triple bond was going to have the highest bond energy. Now let's go to question number 1.2. Now they were saying, consider the following compounds and their respective boiling points. You are given helium, hydrogen bromide, hydrogen fluoride, and they are saying the boiling points, we have got a more negative, a lesser negative, and a positive. So it simply means that this is the greatest. So the boiling point is increasing as we go down. And then now they are saying the correct arrangement for the decreasing strength of the intermolecular forces of the given compounds is. So we know that the higher the boiling point, the stronger the intermolecular forces. So what we know is the higher the boiling point, the stronger the intermolecular forces. So strength is directly proportional to the what? Is directly proportional to the boiling point of the what? Of the compound. So here they said we should arrange these three in accordance to the decrease in the strength of the intermolecular forces. So we are going to take the one with the highest. So this one would be on position number one, this one on position number two, this one on position number three. So the option that we are looking for is the one with hydrogen fluoride, hydrogen bromide, and helium. So that was going to be option C. That being the case, now let's go to 1.3. 1.3 is saying, which one of the following is not a property of the ideal gas? So we know that for ideal gases, there are no forces of attraction between the molecules. This is correct. And then for ideal gases, the collisions between molecules are elastic. This is also correct. The volume occupied by the gas, we know that it is negligible. We usually assume that ideal gases, they have no volume. It is negligible. So here they're saying the volume occupied by the gas is equal to the total volume of the gas molecules. This is not true. And we know that the density of the ideal gas is low. Yes, this is true. So the only option which is not a property of the ideal gas was going to be option C. Now let's go to the following question. So here they are now saying 1.4, the molar mass of hydrated oxalic acid, which is given there, is 126 grams per mole. Now they're saying the number of water molecules present in the hydrated compound is. So we need to use this formulation, which is the molecular formula, to find X, which becomes the number of moles of what? Of water molecules in the hydrated compound. So we know that if I come and then I say the molecular mass of what? COOH times 2 plus X times the molecular mass of my water should actually give me 126 grams per what? Per mole. So now, what is the molecular mass of this compound in here? It is 12 for carbon, and then I've got 2 oxygens, which I've got 16, so that is 32. If I say 16 plus 16, that gives me 32, plus for hydrogen, which is just 1. So if I say 12 plus 32, that is 44 plus 1, 45. So here I'll be having 2 times 45 times X. And then for water, I've got 2 plus 16, which is for oxygen. That gives me 18. So here I would be having 18, which should be equal to 126. So I can actually get to transpose that. So it will be X times 18 is equal to 126 minus, if I say 2 times 45, it gives me 90. So this is equal to 36. So if I say 126 minus 90, it will give me 36. Now, if I now want to find X, I just divide by 18. So if I divide by 18 this side, this will cancel out. If I divide by 18 this side, this will be equal to 2. So X there was equal to 2. That is the answer, which is corresponding to B. So our answer there was supposed to be B. Now allow me to wrap this so that we can see the next question. So that is how you actually get to what? To calculate either your total molecular mass or else to calculate the number of moles of what? Of water of hydration. Now let's look at 1.5. 10 moles of zinc are allowed to react with 5 moles of hydrochloric acid in a test tube according to the balanced equation, where you have got 1 mole of zinc reacting with 2 moles of hydrochloric acid to form 1 mole of zinc chloride and 1 mole of hydrogen. Now they are saying how many moles of hydrochloric acid and zinc chloride is in the test tube after the completion of the reaction. So we can see that we actually require 2 moles of hydrochloric acid to react with 1 mole of zinc so as to form 1 mole of what? Of zinc chloride. So if I have got 5 moles of hydrochloric acid and 10 moles of zinc, it simply means that hydrochloric acid would actually be our what? Our limiting agent, which is going to be consumed before the reaction, or else it is going to be consumed by the reaction completely, so that when it is all consumed or completely consumed, that's when our reaction stops. But we are going to be having some zinc which would be left. So if that is the case, now they want us to determine the number of moles of hydrochloric acid and zinc chloride that will be left after the completion of the reaction. There won't be any hydrochloric acid left, so we have got 0 for hydrochloric acid. Now we need to decide for what? For zinc chloride. Now I'm saying if I've got 5 moles where I require 2 moles to form 1 mole of zinc chloride. When I've got 5 moles, I would actually get to form what? Half of these 5 moles, which is 5 over 2. That would be 2.5. So here I would form what? 2.5 moles of zinc chloride. So our answer there was just going to be B. So we just get to use and play around with the mole ratio there. Now we are saying which one of the following is the conjugate acid of what? Of HPO4 2 minus. So the conjugate acid of this is just going to be what? H2PO4 2 minus. So we are just looking for what? For B there. That one is actually incorrect because it has got only 1 minus at the end. So pay particular attention to that. So here we are going to look for what? For D. So our answer there was going to be equal to what? our answer there was just going to be equal to D. Now let's go to the following, which is 1.7. Now 1.7 is saying consider the potential energy versus distance curve below. They are now saying at point A, the repulsive forces are stronger than attractive forces. So let's look at this graph. So we know that on your left, you'll be having your what? Your repulsive forces being greater than the what? The attractive forces. So this side, you have got your what? Your repulsive forces. And then this side, you'll be having your what? Your attractive forces being greater than the repulsive forces. And then here you'll be having what we refer to as what? Equilibrium point. This would be your equilibrium point where you'd be able to determine the what? The bond length. So B represents what? Bond length. And then, so on A, you would have your repulsive forces being greater than your attractive forces. And then on D, you would be having your attractive forces being greater than your what? Your repulsive forces. Now, let's look at the options that you are given here. They are saying at point A, the repulsive forces are stronger than the attractive forces. This is true. At point B represents bond length. This is true. At point C, net attractive and repulsive forces is zero. Yes, this is true. Where we have got equilibrium, we are saying that the repulsive forces are now equal to what? To attractive forces. Hence, therefore, the net attractive and repulsive forces there would be equal to zero. They will cancel out. So they are saying which of the above statements regarding the above curve is correct. All of the three, they are correct. So our option there was going to be D. Now let's go to 1.8. Which one of the following indicates the correct color of phenolphthalein in hydrochloric acid and sodium hydroxide? What is this compound? This is a pH indicator, which we know that it is colorless in acid, and then it actually gets to turn its color to what? To pink when it is now in a solution that is having a pH that is greater than what? 8.3, which is what we refer to as basic solution. So under acidic solution, it is colorless, and then under basic solution, it is actually what? Pink. So here they are saying which one of the following indicates the correct color of phenolphthalein in hydrochloric acid and in sodium hydroxide. This is acidic, so in acidic it will be colorless. This is a strong base, so it will be what? It will be pink. So our option there, or else our answer was going to be what? Was going to be B. Now let's go to 1.9. 1.9 is now saying which one of the following solutions will have the lowest pH if all solutions have the same concentration. So the lowest pH is that of an acid, and we need to have a stronger acid. So the strongest acid will have the what? The lowest pH. The strongest acid will have the lowest pH. Now let's look at the given option. We can see that option C is out because this is basic, and as well as option D, they are out because they are basic. Now let's look at the two options, A and B. They are both acids. How do we determine which one is the strongest acid and which one is the weakest amongst the two? The one that has got more concentration of what? Of H plus ions. So we can use the what? We can use the definition from Arrhenius' definition of acids, the one with more H plus ions. So we can see that sulfuric acid is a what? It's a diprotic acid. It has got more. It has got 2 times H plus. Whereas HCl, it has got only 1 H plus. So the one which has got the what? Which is the strongest acid there, it's actually what? It's actually sulfuric acid, which is A. So our option there was going to be A. Now we are on 1.10. Consider the following statements regarding a reducing agent. Consider the following options regarding a reducing agent. the substance that causes reduction. Yes, a reducing agent is a substance that causes what? Reduction. And then the substance that is reduced, no, the substance that is reduced is actually what? An oxidizing agent. And then the substance that is oxidized, yes, the one that becomes oxidized becomes the what? The reducing agent. Now they're saying which of the above statements regarding the reducing agent is correct. We have got option number 1 and 3. So statement 1 and 3 only. So we're going to say option D. Now let's look at our open-ended questions, which is from question number 2. And let's see what is it that they were expecting from us. They are saying, consider the following compounds that are given here. We've got iodine, we've got HOCl, we've got ammonia, we've got hydrogen sulfide, we've got potassium bromide. They're saying define a covalent bond. A covalent bond is a chemical bond that involves the sharing of what? Of electron pair, or else that involves the sharing of electrons. So the chemical bond where you have got two atoms sharing electrons, that is what we call what? That is what we call a covalent bond. So it is a chemical bond that involves the sharing of electrons between two atoms. Between two atoms. Between two atoms. So that is what we refer to as a what? As a covalent bond. A covalent bond is simply defined as a chemical bond that involves sharing of electrons between two atoms. Now they're saying write down the formula of the compound from the given list that is a nonpolar. So we know that a nonpolar compound is found or else is formed between two identical atoms. So whenever we've got two identical atoms, we know that these atoms, they've got the same electronegativity. They have the same electronegativity. Once they've got the same electronegativity, then the type of bond that they are going to form there, it will be non-polar, because the sharing of electrons would be what? It will be the same. There is no atom that is going to pull more electrons towards itself. So we have got iodine, where we have got iodine bond. So iodine molecule is a non-pole. So for 2.21, you are going to what? To choose iodine. Now they are saying write down the formula of the compound from the given list that forms a bond as a result of transfer of electrons. Where there is transfer of electrons, we actually get to form what we call an ionic bond. So we know that an ionic bond occurs between a metal and a what? And a non-metal. So we need to identify where there is a bonding between a metal and a non-metal. This is where we have got potassium plus what? Plus bromine. Where we know that bromine is a non-metal, while its potassium is a what? It's a metal. So electrons will be transferred from potassium to what? To bromine. So here we're just going to choose what? KBr. That is where we have got what? Electron transfer. Now they are saying choose where we have got one lone pair of electrons. Where we have got one lone pair of electrons, it is on what? On ammonia. Why? Because where we have got ammonia, ammonia has got 5 valence electrons. So here it is going to share one with hydrogen, one with hydrogen, one with hydrogen. So 3 of its electrons will be shared amongst the 3 hydrogens, and then 2 of its electrons will remain as a lone pair. So here we're going to choose what? Ammonia. And then they are saying which one is a pure covalent bond. Where we have got a pure covalent bond, what is it that we mean by a pure covalent bond? So we are saying that where we have got a pure covalent bond, this is where we have got what? This is where we have got identical sharing of what? Of electrons. There are no any dipole or else any ion dipole induced. Where we have got what? Where we have got equal sharing. Where there is equal sharing, let me just get to write it down. A pure covalent bond is when we have got equal sharing of electrons. Equal sharing of electrons. That is what we mean by a pure covalent bond. Equal sharing of electrons. And we can only have an equal sharing of electrons when we have got what? Identical atoms bonding together. So here we're also going to choose what? Iodine. So those were the options that we were supposed to choose from. Now let's go ahead and let's answer 2.3. 2.3 is now saying draw the Lewis structure of the following compounds HOCl. So for this one, we have got an oxygen atom being the central atom, and we have got hydrogen this side and chlorine this side. So chlorine brings an electron for it to share one from oxygen, as well as hydrogen brings an electron so as to share one electron from oxygen. But we know that oxygen has got what? It has got 6 valence electrons. So we would be left with what? With 2 lone pairs there. So that is how you draw the what? That is how you draw the Lewis structure of what? Of the Lewis structure of that compound. And then here they are saying that uh, here they are saying we have got H2S. So here they've got H2S, which is hydrogen sulfide. So we need to draw the Lewis structure for hydrogen sulfide. So we have got our sulfur that is bonded to what? That is bonded to hydrogen as well as another hydrogen. So our hydrogen brings an electron. It shares an electron from the what? From the sulfur, as well as another hydrogen brings an electron, shares another what? Electron from sulfur. So being the case, that is how you would have drawn the what? The Lewis structure. At some point in time, some they just get to use dots. They don't use the cross there. But I use a dot and a cross. Why? To differentiate that this electron comes from hydrogen and this one comes from sulfur. Or else to differentiate from the electrons that are coming from the other atom. But you can either choose to do either. It's up to your choice. Which one do you actually get to prefer? But both of them, they are correct. Now we are saying the ammonium ion, which is NH4 plus, is formed from ammonia. So we know that here, this is where ammonia reacts with what? With the hydrogen ion to form an ammonium ion that is carrying a positive charge. They are now saying identify the bond responsible for the formation of what? Of ammonium. What is the bond that is responsible? We know that this is what we call dative covalent bonding. Dative covalent bonding. What do we mean by dative covalent bond or bonding? We are just saying that here we have got this hydrogen what? This hydrogen ion carrying an empty shell without electrons. Whilst ammonia has got what? It has got a lone pair of electrons. So you would see that since hydrogen is just carrying an empty shell, it is going to share that lone pair of what? Of ammonia. So these two, they are dating in a sense to say they are sharing the same lone pair that is coming from what? That is coming from ammonia. So that is what we refer to as dating or coordinate covalent bonding. You can call it coordinate. Coordinate from saying they are coordinating on the same lone pair of what? Of electrons. So we call it what? Coordinate bond, or else dative covalent bond. So that is the bond that is responsible for the formation of what? Of ammonium there. After we've said that, now let's look at 2.42. Allow me to just get to rub here so that we can have more space and see clearly our question. They're saying use the Lewis structure to show the formation of what? Of NH plus from NH3. So the Lewis structure just represents what? Either the dot diagram or else the dot and cross diagram. So let's say that I've got ammonia here where I've got hydrogen being bonded with nitrogen there and another hydrogen here, and then I've got a what? A lone pair of what? Of electrons there. So with that, I will react with what? With hydrogen. That is no what? That is no any electron. That is just carrying an empty shell. And then after that, this hydrogen is going to come and share the what? The lone pair of what? Of nitrogen. That is among what? That is among ammonia. So this is how you would have just represented it. But for it to make sense, this is why I would come and say this is an X and that one is an X. Why would I be putting an X? To differentiate between the electrons that are coming from nitrogen from the one that are coming from what? From hydrogen. So that here when you now have got this dative bonding, you can simply see that this hydrogen brings no electron, but it is just sharing the ones that are there. So this is how you would have just shown it. And then at the end of it, you would show a positive what? A positive charge to show that this is a positive ammonium ion. So that is what was expected of you there. After saying that, I'm sure we have seen how we can actually get to form that. Or else just allow me to repeat that same for the sake of others, whilst I actually get to create space for the coming questions. So we are saying hydrogen will be bringing one electron to nitrogen, and then another, and then another hydrogen as well here, and then we'll be left with the lone pair. And then we have got hydrogen that has no electrons, it has got an empty shell, it reacts with ammonia, and then it will only come and share these electrons, which is a lone pair, whilst its other or else its friend, the other friends of this hydrogen, they actually bring something to the table. So that would be the what? That actually would be the Lewis structure of the formation of what? Of an ammonium ion. So that being the case, let's go to what? To 2.5. Now they're saying write down the molecular shape of HOCl. So from this Lewis structure, we can see that we have got what? We have got two lone pairs and two electron pairs being shared. So this actually transfers to a what? To a trigonometric pyramidal shape. So this becomes a trigonometric pyramidal shape. So I'm assuming that we know that the one that is actually having, let's say, just two electron pairs, it is actually a linear, that would actually get to say what? It is a linear shape. From that linear shape, when we have got three electron pairs that are being shared, we go to a what? From linear, we go to a trigonometric shape. From a trigonometric shape, that's when we now go to a what? Trigonometric pyramidal shape, where here we have got what? Three electron pairs that are being shared. That's why we call it a trigonometric from a triangle. And then when we now have got two lone pairs and two electron pairs, we now call this a trigonometric what? Pyramidal shape. And then from there, when we now have got four electron pairs that are being shared, we call this a what? A tetrahedral shape. So that one is called a what? A tetrahedral shape. And then from there, we go to a pyramidal shape. From a pyramidal shape, we go to an octahedral shape. So I'm sure we remember the naming of these shapes from the what? From the electron pairs and the lone pairs. Now for ammonia, I have got three for ammonia. So this actually here I misplaced. We said from linear, we should go to what we refer to as bent, because here I would be having an oxygen that is having my hydrogen here, and then that will be having a chlorine there. And then after that, it will be left with what? With two lone pairs. So we call this a bent shape. And then the one that would be now having, let's say it is having something that is like ammonia, that has got hydrogen, another hydrogen, another hydrogen, which is three electron pairs, and then a lone pair, maybe a lone pair there. This is what we call trigonometric pyramidal shape, where we have got this trigonometric shape from these three electron pairs, and then the pyramidal is coming from the what? From the lone pair. So this would call it a what? A trigonometric pyramidal shape. So just pardon me there. I'd actually what? I'd actually interchanged this. From linear, we go to bent. From bent, we go to trigonometric, where we have got only three electron pairs. From trigonometric, we go to trigonometric pyramidal shape. From trigonometric pyramidal shape, that's when we now go to tetrahedral. From tetrahedral, that's when we go to pyramidal. From pyramidal, that's when we go to octahedral. So this one would be having a bent shape because it has got what? Two lone pairs as well as two electron pairs. And then from the bent shape, this one has got three electron pairs and one lone pair. So this one would be trigonometric pyramidal shape. So those are the two shapes of those two compounds. Now let's go to 2.6. Will iodine be soluble in uh, carbon tetrachloride? Will iodine be soluble in what? In carbon tetrachloride? Write down yes or no. The answer here is supposed to be yes. Now, why is it a yes? That is a question now to say why will it be a what? A yes. So you would see that when we take carbon tetrachloride, you would see that it will be a bonding between what? Carbon, chlorine. So the bond between carbon and chlorine, it is actually a what? A polar bond, because this is more electronegative than carbon. So you would have a partial positive here, and then you would also come to have a partial positive there, a partial positive there, a partial positive there. So you would see that electrons will be attracted towards, or else they will be drawn more towards the chlorine. So you would see that if that being the case, when we now want to look at what we refer to as the overall shape, because we are saying that on opposite sides we've got what? The chlorine pulling the electrons towards itself, you would end up having what we refer to as what? As a linear shape. Due to this linear shape, because there is no way we have got electrons uh, being pulled towards, or else a side which is prone to have more electrons than the other, we are going to have a what? A non-polar. We are going to have a non-polar what? A non-polar bond. So this being a non-polar, we know that from the solubility rule, we know that a non-polar solvent dissolves only what? Non-polar solutes. And then a polar solvent dissolves what? Polar solutes. So we are saying that a non-polar solvent dissolves what? It dissolves non-polar solutes. That is the rule of what? Of solubility there. If that being the case, if that being the case, we also get to say what? A polar solvent dissolves polar solutes. So now you would see that iodine is also what? Non-polar. Iodine, we have actually determined that it is what? Non-polar. Why? Because it is just a bond between two identical atoms. So we have got a non-polar solvent and a non-polar solute. So definitely iodine is going to what? To dissolve in what? In carbon tetrachloride. Why? Because they are both non-polar. So after I've said this, they'd say that choose yes or no and explain your answer. So let's just get to write down a clear explanation why iodine would be soluble in what? In carbon tetrachloride. So we are saying that the answer here was going to be yes, it is soluble. And then you come to say that iodine is non-polar, while carbon tetrachloride is also what? Non-polar. And we know that non-polar solvent dissolves non-polar solutes. Therefore, iodine will be soluble in carbon tetrachloride. Why are we saying carbon tetrachloride is non-polar? It's because of its overall shape at the end. Its overall shape. That being the case, now let's go to question number 2.8. Now let's go to question number 2.8. 2.8 is saying the following table shows the average bond energies of atoms that are bonded to the hydrogen atom. So these are the what? These are the average bond energies from the what? From the atoms that are bonded to hydrogen atom. Now they're saying define the term bond energy. So we know that bond energy is the minimum energy that is required to break a bond, to break a chemical bond, let's say, to break what? A chemical bond, to break a chemical bond. Others would come and say that it is the energy. They would say that 2.81, they would say it is the energy that is required to break one more to break what? To break one more of its molecules into separate atoms. So we are just saying that the amount of energy that is required to break this carbon hydrogen bond that is existing here so as to form separate atoms like carbon and hydrogen. That minimum energy that you require, that is what we refer to as what? As the bond energy. So now they are now saying explain the trend observed in the bond energy in the table above. How do we explain the trend that is observed here? So you can see that carbon, oxygen, and fluorine, they are in the same period. These ones, they are in the same what? In the same period. Meaning to say that they are arranged as to say carbon, oxygen, and fluorine. So as we go towards the right of a period, we know that the atomic radius of our atoms, it actually gets to what? It actually gets to decrease. Why does it decrease the atomic radius? It actually gets to decrease because the nuclear charge here increases. We know that the nuclear charge increases. That means that the attraction of outer valence electron increases from the what? From the nuclear what? Positive charge. So as this atomic radius decreases, we know that it will actually get to what? It would actually get to shorten the bond length. So we know that the bond that would actually be made with other atoms would actually what gets to shorten. So the bond length will shorten. So as the bond length shortens, it simply tells us that the bond energy would actually guess what? It will actually get to increase. It is actually harder, or else it requires more energy to break down a shorter bond length than a what? A longer bond length. Because a shorter bond length, it simply represents that these two atoms, they are close towards each other. So the attraction of what brings them together is very strong. So we are saying that from carbon to oxygen to fluorine, the atomic radius is actually what? It is actually decreasing. As the atomic radius is decreasing, the nuclear charge is increasing. Hence, therefore, the attraction between the carbon atom or else between these atoms with the hydrogen atom would actually get to what? To increase going towards the right of the period because of the what? Of the shortening of the bond length. So that is the reason why we have got carbon hydrogen having a lesser what? Having a lesser bond energy than fluorine hydrogen. So that is what you would have just came and explained there to say that, let me just get to explain it here. To say that you would say 2.82 carbon, let's say oxygen and what? And fluorine. They are in the same period. And then you say that across a period, across a period from left to right, comma, the atomic radius of atoms in the period decreases, comma, which increases the nuclear charge of the atom. And then you would also come and say, this therefore leads the atom to forming shorter bond length with other atoms. And then you get to say that as the bond length becomes shorter, the bond strength increases. So we know that a stronger bond requires what? A higher bond energy. So that is what you would have said, because you are just describing the trend that you have been given. They're just asking you, why is it that the bond energy is increasing across the period when these elements are actually reacting with the same what? They're actually bonding with the same atom. So that is how you explain it. Now let's look at question number 3.1. They are saying learners investigated the boiling points of the compounds listed in the table below. And now they are saying we have got compound A, B, C, and D. And you can see that these, they are from the same group, which is usually what we refer to as group number 4. Why? Because they've got a valency of what? Of 4. A valence of electrons of what? Of 4. Maybe I can say a valence of 4 electrons. So the outer electrons within this group of elements, which is carbon, and then we have got what? Silicon, germanium, and tin. They have got a valence of 4 electrons. Now they are saying define boiling point. This is the temperature at which uh, the vapor pressure of a compound is equal to the atmospheric pressure. Once the vapor pressure is equal to the atmospheric pressure, once the vapor pressure of a compound is equal to the atmospheric pressure, this is when you now start seeing that compound starting to break away from the form of a liquid into a gas, because it has actually gained enough molecular energy to actually get what? To escape the liquid form. So the boiling point, we define it as the temperature at which the vapor pressure of a compound is equal to the atmospheric pressure of that same compound. Sorry, to the atmospheric pressure that is outside of the what? Of the container in which it is being boiled in. Now we are saying, is this a fair investigation? Write only yes or no on top here. So we can agree that yes, this is a fair investigation. Why? Because we only have got only what? One variable being changed there. These are from the same group, and the only thing that is changing is we are going down the group, which is increasing the molecular what? The molecular mass of each element. So only the atomic mass or else the molecular mass is changing. So this investigation is actually what? It's actually fair. Give a reason: because only one variable is being changed or varied. Only one variable is being changed or varied. That would be your explanation there. Now they're saying write down the phase of the above compounds at room temperature. So you can see that at room temperature, uh, the boiling points tells us the temperature at which these compounds, they transform from liquid to gas. So under these, below these boiling points, these compounds are liquids, but above them they are gases. So you can see that the minimum, or else let's say the maximum boiling point there that we have, it's actually equal to what? Negative 52 degrees Celsius. And room temperature conditions are at least 25 degrees Celsius. So we can simply see that 25 is greater than what? It's greater than negative 52. So these compounds, there will be a gas at room temperature. So you'd have just came and said what? Gas phase at room temperature. Why? Because you can see that room temperature is above the what? The highest boiling point of these compounds. So that is what you would have just said there. After we have said that, let's get to see the coming question. So allow me to create space. Now they are now saying explain the trend observed in boiling points of the compounds in the table above by referring to the molecular mass, intermolecular forces, and the energy involved. So they now want you to explain this experiment in terms of the what? Of the molecular masses and the energy involved. So we are saying that from what we can see, the boiling points increases as we go down the what? The group. because we know that carbon is on top of the group going down. So the boiling point is increased as we go down the group. That means that the boiling points are increasing as the molecular mass is increasing. So what's the relationship between the molecular mass and the intermolecular forces? We know that as the compound becomes bigger, or else when it becomes heavier, it has what? Strong intermolecular forces. So it will require more energy to actually get to what? To boil it. So that is what we're just going to say here. You're just going to come and say 3.4 are the boiling points are increasing as we go down the group. Full stop. This indicates that as the molecular mass increases, also the boiling point increases. This is due to the fact that as the compounds become heavier, the intermolecular forces between them become strong. So you were just supposed to show that there is a relationship between the boiling point and the molecular mass of these what? Of these compounds. So as the molecular mass is increasing, the boiling points are also increasing. This is an indication that boiling point is directly proportional to the what? To the molecular mass. So why is it that? It is because we know that as the compound becomes heavier, the intermolecular forces they also get to what? To become strong. And we know that boiling point is directly proportional to the what? To the intermolecular forces. You would say, and boiling point is directly proportional to the intermolecular forces. Intermolecular forces. So we are saying that the boiling point of a compound is directly proportional to the what? To the intermolecular forces of that compound. As the intermolecular forces become stronger, the boiling point will also get to increase. That is the reason why we have got this trend. Now they're saying which compound in the table above is the highest vapor pressure at a given temperature. Explain the answer by referring to the data that is given in the table above. So we know that vapor pressure is inversely proportional to the boiling point. The compound with the lowest boiling point, it has got what? A higher vapor pressure. So this one has got what? It has got the highest vapor pressure. And this one has got the what? The lowest vapor pressure. Why? Because we know that vapor pressure is inversely proportional to the what? To the boiling point of the what? Of the compound. So here you would have said, they said which compound is in the table has got the highest vapor pressure. You would have chosen what? You would have chosen methane, which is CH4. Why? Because you know that vapor pressure is inversely proportional to the what? To the boiling point. So you would come here and say 3.5 vapor pressure is inversely proportional to the boiling point. So the higher, so the lower the boiling point, the higher the vapor pressure. Because we are saying that if you are having a compound, that is what? If you are having a compound that is having a lower boiling point, it simply means that its vapor pressure is high. You would need more and more what? If you are having a what? We are saying that if the boiling point is low, its vapor pressure is high in such a way that once you actually get to reach this lowest temperature, it can actually easily transform into a what? Into a gas. So the highest the vapor pressure, the lowest the what? The boiling point. So methane there would be having a what? A highest vapor pressure. After we've said that, 3.6 is now saying the boiling point of hydrogen fluoride and the one for hydrogen chloride is compared below. And then they are now saying, will the value of X be higher than or lower than or equal to 19.5 degrees? So hydrogen fluoride is here. It is having what? 19.5 degrees. And then we have got what? Hydrogen chloride. They are now saying, is the boiling point of hydrogen chloride greater or smaller than the one for what? For hydrogen fluoride. How do we compare those two? So one thing that we know is this: when it comes to these two, they've got what we call what? Covalent bonding. They are bonded covalently, but however, their bonds they differ in such a way that here we only have got what? We only have got induced dipole intermolecular forces. Whilst here we have got hydrogen bonding. Why? Because fluorine carries a higher electronegativity. So you know that fluorine carries a higher electronegativity. So when hydrogen is bonded to is bonded to an atom that is carrying a what? A higher electronegativity, it forms what we call what? Hydrogen bonds. Hydrogen bonds. It forms a special type of covalent bond which is called what? Hydrogen bonds. And we know that hydrogen bonding is stronger than what? Than any other covalent bonding. So here we have got hydrogen fluoride carrying both hydrogen bonds and what? And dipole bonds. Whilst hydrogen chloride is only carrying what? Dipole bonds. So definitely X would be greater than what? X would be less than what? 19.5. Because we are saying that hydrogen fluoride will be having stronger intermolecular forces. Now they are saying, fully explain the answer to question 3.6. How will you explain the answer that you have given there? We are saying that hydrogen fluoride contains hydrogen bonding, which is stronger than any other covalent bonding, while hydrogen chloride contains dipole van der Waals forces, dipole what? Intermolecular forces. Or let me say that bonding, which is governed by what? By these van der Waals intermolecular forces, which are weaker than what? Which are weaker than the hydrogen bond. Hydrogen bonding intermolecular forces, which are weaker than the hydrogen bonding what? intermolecular forces. So hence, therefore, the boiling point of hydrogen fluoride will be greater than the boiling point of what? Of hydrogen chloride. That is the simple what explanation that you can give. In hydrogen fluoride, there are hydrogen bonds, or else there is hydrogen bonding. Whilst here there is only what? Dipole, dipole what? Covalent bonds. Of which you know that hydrogen bonding forces, or else hydrogen bonds are stronger than what? Dipole covalent bonds. So that was the explanation that we are going to give there. Now let's look at question number 4. Question number 4 is saying learners investigated the relationship between pressure and volume of a gas. The graph below shows the results obtained during the investigation. This is the what? The graph that is given, that is showing the results from that investigation that the learners did. Now they are saying name and state the law that the experiment is based on. So here we can see that volume is inversely proportional to the pressure. The higher the volume, the lower the pressure. So this is actually what? Boyle's law. And then they're saying write down a hypothesis of this investigation. We just get to say the higher the volume, the lower the pressure. That is the hypothesis, or else that is the simple observation that you can make out of the results. That's what they want you to say. When they say the hypothesis, they are saying what simple observation or else conclusion can you make out of the what? Out of the gas that is, out of the graph that is given. So here I can see that here they said state and what? They said name and state the experimental law. Let me just get to name and state that I only named, I did not state the law. So on 4.1, you would have said it's what? It's Boyle's law. And what does Boyle's law say? It says that if a confined gas or else enclosed gas, if a gas is confined, if a gas is confined, if a gas is confined, is confined or else is enclosed, and held at constant temperature, then its volume varies inversely to its pressure. So the law states that if a gas is confined or else if it is enclosed within, let's get to say within a container, and then we actually get to keep the temperature constant, it simply means that if I'm to actually get to what? To either compress or else expand the what? The gas, it simply means that the volume of the gas is going to vary inversely proportional to the what? To the pressure of the what? Of the gas, which is given by the law which says what? PV is equals to a constant. That is what it simply states there. And then the hypothesis is that the higher the volume, the what? The lower the pressure. So on 4.2, you would have just said the higher the volume, the lower the pressure of the gas. That is what you would have said in terms of what? Of the hypothesis that you would draw out from that what? From that graph. Now let's see and hear what they actually gets to say next. Now they're saying read and write down the pressure of the graph when the volume is 12 cubic centimeters. So here the volume is given in cubic centimeters at 12. This is where we are. So the pressure there at 12 cubic centimeters, we've got a pressure at what? 40 times 10 to the power 3 pascals, which is just 40 kilopascals. That is what you would have said. So that was going to be the answer for what? For 4.3 there. You were just going to come and actually get to read a value that is corresponding directly with what? With 12 cubic centimeters. Now they are saying calculate the volume of 200 kilopascals. Now, from this law that I've said this side, where I say that the law that governs there, it's actually what? The law that governs there, let's say for 4.4. Its PV is equals to a constant, which simply means that P1 V1 would be equal to P2 V2. So if I know pressure 1 and volume 1, which is actually what? Which is actually 40 kilopascals, 40 kilopascals, and I know the volume, which is 12 cubic centimeters. Then if I know the pressure P2, which they gave us 200 kilopascals, I would be able to find V2 in cubic centimeters. So I'll just divide by what? By 200 both sides. And that would actually get to cancel out the side. So my volume in cubic centimeters, I would simply say 40 times 12 and then later divided by what? By 200. It is going to be equal to what? It is going to be equal to 2.4 cubic centimeters. So when my pressure is 200 kilopascals, my volume there would be equal to 2.4 cubic centimeters. So you can see that as my pressure increases, my volume decreases. Now they're saying redraw the above graph and label it A. On the same set of axes, draw the graph to show how a real gas will deviate at higher pressures. Label this graph B. So at higher pressures, an ideal gas ceases to being an ideal gas. It now becomes a what? A real gas. And when it becomes a real gas, we know that PV now of the what? Of real gases is actually greater than what? PV of ideal gases. So it comes to where you would actually get to see that at higher pressures on this graph, let me just get you to this. At higher pressures, you would see that this graph will now start going to be a constant. Maybe let me just get to say that it will start having something like this, where this will be the graph of B. I'm just saying that PV of graph A will be less than PV of graph B. So at higher pressures, we are now saying that we are now moving to a constant, or else now we can see that the relationship is deviating from the ideal gas, where you would see that at some point in time it will cease to follow this law. It will now cease to follow that law. It will be going against this law. So you are just going to draw this graph as it is, and you label this A, and then you draw a graph like this, where we are now saying at higher pressures. Now the higher pressures, you can take them maybe from 100 kilopascals to say that above 100 kilopascals, this is where now you will start having what? A deviation from the what? From the ideal gas law there. Because we know that Bohr's law, Chau's law, they are all derived from what? From ideal gas behavior. Now let's go to question number 5. Question number 5 is saying, consider the decomposition reaction of what? Dinitrogen pentoxide, which is this one. The table below shows the different energies for the above reaction, which is to say heat of the reactants. This is the heat of reactants. It's given activation energy and the heat of the what? Of the heat of the change of reaction. That is to say this is equal to H products minus what? H reactants. And this is actually a negative. So therefore, it shows us this is an what? This is an exothermic reaction before any questions can come. Now they're saying define the term activation energy. This is the minimum energy required to initiate a reaction. Minimum energy required to start or initiate a reaction, to start a chemical reaction. So for a chemical reaction to commence, we require some minimum energy. It's more like when you want to combust or when you want to make a fire, you need to first scratch maybe from the matchbox, and then that's when you will start making some flames. So that is the minimum amount of energy that you are talking about. For there to be that, for there to be a chemical reaction, that flame that you get to see, that's what we refer to as the what, as the chemical reaction occurring. We need that scratching that becomes our minimum energy. Is the above reaction endothermic or exothermic? It is exothermic, as we have said. Why? Because we can see that our delta H is a negative. It shows that the enthalpy of reactants is actually greater than the enthalpy of what? Of products. So this is actually an exothermic reaction. So here you're going to say it is actually an exothermic reaction. Why? Because enthalpy, or else let me say that the heat, let's just use the values that are given there. It would be simpler like that. Heat of the reaction, which is delta H, is equal to a negative. Once we have a negative, it simply means that HP of reactants is greater than what? HP of products. So we have got more energy in the reactants than in the products. So our reactants are losing energy. That's why we are saying it's exothermic. They are emitting what? They are emitting energy. Now they're saying calculate the heat of products. The heat of products now, let me just get to do it this side. So from the reaction that I've given you there, let's say 5.3, I know that HP of products minus HP of reactants would be equal to the change in what? In the enthalpy of reaction. Where now the change in the enthalpy of reaction is what? Negative 7.28 kilojoules. And then the enthalpy of your reactants is actually what? It's actually 26.6. So the enthalpy of products would be equal to negative 7.28 plus 26.6. So what becomes the enthalpy of products there is just the difference of those two, which will give you 19.32 kilojoules per each mole. So that becomes the enthalpy of products. That is how you calculate your enthalpy of products. From the formulation that says enthalpy of products minus enthalpy of what? Of reactants. Now they're saying draw the potential energy versus cost of reaction graph of the above reaction. So I would actually get to say for the above reaction, I would use this to draw that graph. So you know that for me to draw that graph, I would be having time, which is progress of my reaction, and then I'll be having my potential energy this side, which can be in kilojoules per mole. And then I will take the enthalpy of reactants to be here, going up to our activation complex, and then later coming back to our reactants, to our products. Why? Because we are saying products, they've got lesser enthalpy of what? The enthalpy. So we have got our products here, which are having a certain value of what? We say that this value is 19.32, and this value of product of reactants is what? It's 26.6. So here we have got our what? Our reactants. And then here we have got the activated complex. The activated complex. Now, we know that the difference from our reactants to our activated complex, this difference is called the activation energy. So if I say HP of my reactants plus my activation energy gives me what? H of my what? Of my activation activated complex. It gives me H of my activated complex. So maybe I can represent that by H of what? Activated complex. If that is the case, this is my peak. So I would say enthalpy of reactants is 26.6. What is my activation energy as it is given there? My activation energy here is given as 6.6, 6.73. 6.73. So here I'm going to have what? I would add 6.73. And then this would be in kilojoules per mole. That is H of my what? Activated complex. Now, 26, if I say 26.6 plus 6.73, that gives me 33.3. So this becomes 33.33. So here I've got my activated complex at 33.33 there. If that is the case, now what is it that they say that I should show? They say that I should show heat of reactants, H of reactants. This is the H of reactants. Maybe I would come and indicate using another color. So this is HR, heat of reactants. Heat of products, this is my what? My H of products. So that is my H of products, this one. And then they said I should show energy at the activated complex. This is the energy at activated complex. At activated complex, which is this one. And then they said I should show heat of reaction, which is change in what? So this change would be given by this two, the difference there. So that becomes the enthalpy of reaction, the enthalpy or heat of reaction, that difference in between HR and HP. I've shown those. So that is how you are going to draw your what? Your graph there. And now they're saying on the same graph drawn in question 5.4, use a dotted line and draw the shape of the graph when a catalyst is added to the original reaction. So the main purpose of a catalyst is to lower the activation energy. So I would have just came there and draw something like this, something that lowers my what? Something that lowers my activation energy, but it gives me the same what? The same products. So that would have been with catalyst. That is the graph that you are going to draw there. So that would have been the final graph, just like that. That is what you expected to draw there. So if that is the case, now let's go to question number 6. So question number 6, it is now saying compound Q, which is CXHY. This one is it's a carbohydrogen, or else they call them what? Organic compounds. It reacts with oxygen according to the following balanced equation. So it's a hydrocarbon. It's reacting with oxygen. So I assume that this is a combustion reaction to form carbon dioxide plus what? Plus our water. Now they're saying the molar mass of compound Q, this compound, is 58 grams. Now define the empirical formula. The empirical formula is the simplest atomic ratio, the simplest whole number atomic ratio. So you would say whole number atomic ratio, the simplest whole number atomic ratio, comma, in a compound, or else of a compound, the simplest whole number atomic ratio of a what? Of a compound. That is what we refer to as what? As an empirical formula. Now they're saying use the principle of conservation of mass and determine the value of P. The principle of conservation of mass, it simply states that mass in should be equal to mass out. So 6.12 there, I would come and say 6.12. I know that mass in should be equal to mass out. So the mass that is in our reactants should be equal to the mass that is in our what? In our products. So here they are saying that Q, which is this, has got 58 grams. So I would come and say P times 58 grams because these are the number of moles that are reacting. So the number of moles of this hydrocarbon that are reacting times its molar mass plus the number of moles of oxygen atoms that are reacting times the molar mass of oxygen, which is 32, should be equal to, I've got 8 times of carbon dioxide, that is 12, plus 32, that becomes 44, plus 10 times of water, that becomes 18. So if I want to know the value of P here, I'll take this, I transpose it to that other side, I'll be left with P times 58. And then this actually becomes, if I say 8 times 44 times plus that, it becomes 8 times 44, that is 352, plus 10 times 18, that becomes 532. So when I've got 532 here, I subtract 13 times 32. That gives me 416. So if I subtract 416 from 532, I'll be left with 116, 116. And this side I've got what? 58. So when I now want to know P, I'll just come and divide by what? By 58. By 58 this side. So you will see that these ones, they cancel out. My P would be equal to 116 divided by 58. That is simply equal to what? To 2. So we have got 2 moles of this hydrocarbon compound reacting with 13 moles of oxygen to form what? 8 moles of carbon dioxide. So my P there was going to be equal to 2. The value of P was going to be equal to 2. Now they are now saying the percentage composition of the compound Q is given below. Determine the molecular formula of Q. So I can use this percentage composition to determine the empirical formula. After determining the empirical formula, I would now come and determine the what? The molecular formula using the mole mass of this compound. So just allow me to rub some things here, and then I can go and work it out. So I've got 82.76 and 17.24. So here I would come as usual, as I usually advise and prefer, to draw a table where you list down your elements, you list down the total mass of each element, and then you calculate the number of moles, and then you calculate the what? The simplest number of the simplest mole ratio there. The simplest mole ratio, where you now come and calculate the what? The simplest mole ratio there. And then from the simplest mole ratio, that's when you can get your what? Your empirical formula. So we have got an element. So the elements that are there, it's carbon and hydrogen. That being the case, I will take a basis of what? Of 100. Let me just get to say the basis here would be of a mass which is equal to what? 100 grams. So that I say these two, they amount to 100 grams. So the mass composition of carbon is 82.76%. That translates to what? That translates to our mass. That becomes 82.76. And then for hydrogen, that becomes 17 point what? 24. So this becomes 17.24. 17.24. Now the number of moles will be given by mass over molecular mass. And then this one is going to be 82.76 divided by the molecular mass of, or atomic mass of carbon is 12. If I divide there, I should find an answer of 6.90, 6.90. And then 17.24 divided by 1. I would simply find 17.24. If I divide this by the smallest mole ratio there, it's 6.90. I divide by 6.90, I would have 1. I divide this by 6.90, I would get 2.5. Now, I now need the simplest whole number ratio. I need the whole number ratio. I would multiply by 2 here. So I can come and multiply by 2. This would be 5. Multiply by 2. This would be 2. So the simplest whole number ratio would be C2H5. This becomes my what? My empirical formula. Once I have got my empirical formula, I will now get to use my molar mass, where they said this is equals to, so I'll say X times C2H5 is equal to 58 moles. If that is the case, I'll now get to divide by the what? By the molar mass of this, so that I can find the number of moles that I need to actually get to multiply. That becomes my mole ratio. So here I've got 12 times 2 plus here I've got 5 times 1. And then if I combine those and then later divide, if you say 12 times 2, it will be 24 plus 5, that will be what? 29. So this is x times 29 equal to what? 58. If that is the case, I divide by 29. Divide by 29. X would be equal to 2. If I come and multiply by 2 there, my molecular formula would be what? Would be given by, let me just get to say here, my molecular formula would be given by 2 times C2H5. That would be equal to C4H10. That is how I find my what? My molecular formula. I use my empirical formula to actually get to determine the what? The mole ratio there that I need to multiply by. The number of moles that I need to multiply by. After we've said that, now let's go to the next question. So with that, so here the molecular mass that our the molecular formula was going to be C2H10. That was going to be C4H10. So they say that the question was saying determine the molecular formula of compound Q. That was going to be C4H10. Now they're saying 5 grams of sodium carbonate reacts with 250 cubic centimeters of hydrochloric acid in that reaction. The percentage of hydrochloric acid that reacted with sodium carbonate is 76%. Define the term limiting reagent. This is the reactant that gets completely used up. So the reactant that gets completely used up becomes our limiting reactant. Once it has been completely used up, the reactant stops. So here they are telling us that 76% of our sodium carbonate reacted. So it simply means that the limiting reactant is what? Is hydrochloric acid. So hydrochloric acid actually what? It actually reacted all of it. Now they're saying calculate the amount of hydrochloric acid that reacted with sodium carbonate. So here they're saying 5 grams of sodium carbonate reacts with 250 cubic centimeters of hydrochloric acid. So the volume of HCl here is equal to what? 250 divided by 1000. So that we can have 0.25 decimeter cubed. Because our standard units for volume is decimeter cubed. And then now they're saying the percentage of hydrochloric acid that reacted with sodium carbonate is what? Is 76%. The percentage of hydrochloric acid that reacted with what? With sodium carbonate is 76%. If that is the case, I now need to find the number of moles of sodium carbonate that reacted. And then after that, I would be able to find the number of moles of what? The number of moles of hydrochloric acid that reacted. So I can actually get to take this side, and then I can actually get to rub this, because I'm sure I no longer need this. I would come there and say 6.21. I need the number of moles that can be given by mass over molecular mass. which is 5 grams over what? Because now I'm looking at the number of moles of what? Sodium carbonate. Because they said 5 grams of sodium carbonate reacts with that. If that being the case, because here, this is 6.22, not 6.21 amount of hydrochloric acid that I want. So the number of moles of sodium carbonate will be 5 over. For sodium, I actually have what? For sodium, I actually has got 24. I can say 24 plus 12 plus 48. That becomes 5 over 106. And then that gives you what? That gives you the number of moles. If you divide there, you'd have 0.047 moles. Now, this is the total number of moles of sodium carbonate that was present. And they're telling us that only what? And we can see that 1 mole of sodium carbonate reacts with 2 moles of hydrochloric acid. And they're telling us the percentage of hydrochloric acid that reacted with sodium carbonate is 76%. So now they want the amount of hydrochloric acid that reacted with sodium carbonate. So the number of moles of sodium carbonate that reacted becomes what? 0.047. If the number of moles of sodium carbonate that reacted becomes this, we were requiring what? 2 moles of what? Of hydrochloric acid as to 1 mole. So here I would come and say the number of moles of hydrochloric acid that we required were going to be equal to, if we completely reacted what? Our sodium carbonate. We're going to be equal to 2 times 0.047 moles. Now multiplying by 2 there, I was going to get what? 0.094 moles. So that is what? That is the amount of hydrochloric acid that would have reacted with what? With sodium carbonate. So let's just get to recap here. There is something that I want us to understand within this question. They are saying 5 grams of sodium carbonate reacts with 250 cubic centimeters of what? Of hydrochloric acid. And now they are saying the percentage of hydrochloric acid that reacted with sodium carbonate is 76%. So out of 250 cubic centimeters, only 76% reacted. And if we are having 5 grams of sodium carbonate, how much of hydrochloric acid reacted? We calculate the number of moles of sodium carbonate. That is what we did here. And then we found what? 0.047 moles. Now, how much of hydrochloric acid was required to react with this? It will be 2 times the number of moles that we have calculated, which is 0.094. So the amount of hydrochloric acid that reacted would become what? 0.094. 0.094 moles. And then now they're saying calculate the volume of carbon dioxide that was produced. The volume of carbon dioxide that was produced. Take the molar volume at room temperature to be what? 24.45 decimeter cubed. So now I need to simply look for the number of moles of what? Of carbon dioxide that was produced. So 1 mole of sodium carbonate produce 1 mole of carbon dioxide, because this is our limiting reactant, because only 76% of this reacts in our complete reaction. So this is limiting. So we actually relate the number of moles of sodium carbonate to the product. So 1 mole produces 1 mole. So the number of moles here would be equivalent to the number of moles of what? Sodium carbonate. That would be equal to 0.047 moles. If that is the case, we know that number of moles is equal to the volume of the what? Of the compound over the molar volume. So if I now want to know the volume of what? Of carbon dioxide would be equal to the number of moles times the what? The molar volume, which would be simply equal to what? Which would be simply equal to 0.047 times 20 what? 24.45. That would give you what? If you multiply there, you are going to get 1.149 decimeter cubed. That is the amount of what? Of carbon dioxide that was produced. So here we're going to have what? We're going to have 1.149 decimeter cubed. Now, calculate the hydrochloric acid that was used in the reaction. So now they're saying the hydrochloric acid that was used in the reaction was obtained by diluting 100 cubic centimeters of hydrochloric acid to 250 cubic centimeters of what? Of hydrochloric acid solution. Calculate the concentration of the concentrated what? Hydrochloric acid. Right. This is very interesting. So now we are now diluting our hydrochloric acid. We are now diluting our what? Our hydrochloric acid. So initially, what are the number of moles of hydrochloric acid did we have? So we would actually get to say number of moles of hydrochloric acid that we had initially before reaction would be equal to what? To 100% of whatsoever that reacted. Now we are told that only 76% reacted. And that 76% that reacted is equivalent to 0.094 moles. So what is 100%? So 100% would be equal to what? So the number of moles of hydrochloric acid that was available initially is equal to what? 0.094 times 100 over 76. That is going to give you what? Because if 76% is equals to what? To 0.094, what would be 100? It would be 100 over 76 times whatsoever is available there. That gives you what? 0.094 times 100 divided by 76. That gives you 0.124. So this one becomes 0.124 moles after rounding off. So if this is the initial number of moles that we were having, now they're saying the hydrochloric acid that was used in the reaction was obtained by diluting. So this is what we had initially, and this is what was diluted. That is to say, 100 cubic centimeters were diluted in what? In 250 cubic centimeters. What becomes the concentration? What becomes the what? The concentration. So we know that concentration can be calculated by what? Number of moles over the total volume that we had. So we had 0.124 moles initially, and that was what? Amounting to 100 cubic centimeters. So you would come and divide by 100 divided by 1000 there. That will give you 0.124 moles divided by 0.1 decimeter cubed. So the concentration that you are going to find there was just simply going to be equal to 1.24 moles per decimeter cubed. So what we are saying is initially, how much of our hydrochloric acid did we have in terms of moles? We would actually get to say 100 divided by 76 times 0.094, which is equivalent to 76%. And then we get what? 0.124 moles. So these are the initial number of moles of hydrochloric acid that we had initially. And this was amounting to 100 cubic centimeters of HCl, which was later diluted in this volume. So when we want to find the concentration of hydrochloric acid that was concentrated, which was initial concentration before dilution, we would actually get to say the number of moles of what? Of concentrated hydrochloric acid divided by the volume of what? Of concentrated, or else the total number of moles of HCl divided by the volume of concentration. That is to say 0.124 divided by 0.1. That is how we can find this concentration. that is equal to 1.24 moles per decimeter cubed. That is simply what we're supposed to do there. Now let's go to question number 7, and we'll now later do question number 8, and then that will be the end of it. Now they're saying carbonic acid ionizes in water according to the following balanced equation. This is the balanced equation that they've given you. They're now saying define an acid according to Arrhenius theory. So we know that according to Arrhenius theory, an acid is a proton donor. An acid is a substance that produces what? Hydrogen ions, or else that, so we can actually say that an acid is a substance that forms H plus or else H3O plus ions in water. So if you are to actually get to dissolve a substance in water and it forms H plus and H3O plus ions in water, that becomes an acid according to Arrhenius. Now they're saying write down the formulae of the two substances that can act as an ampholyte. An ampholyte can act as both an acid and a what? A base. There is some instances where it becomes an acid and an instance where it becomes a base. So here the first one becomes water, and then what becomes the second one? The second one would actually become what? It would actually become hydrogen carbonate. This can actually be a base when it is in reaction with this, but it can actually be an acid when it reacts with water. So we would actually come and take what? We would actually come and take water and HCO3 minus. Now they are saying write down the formula of two acids from the reaction. From the reaction, this one is the first acid. It will be H2CO3. And then we would have this as another acid. Because this is a reversible reaction, so when it is going to the left, this is donating a proton to this. That is according to Bromstead theory. When it donates a proton, this becomes a diprotic acid. When we are going towards the right, this is donating a proton to water, and then it becomes what? H3O plus. So this one is an acid as well as that. So now we go to 7.14. Balanced equation between carbonic acid and sodium hydroxide. They want us to write a balanced reaction between what? Carbonic acid, which is H2CO3, and what? And sodium hydroxide. So when these two react, they will form sodium carbonate and what? And water. They will form a salt because this is an acid and a base. This is a neutralization reaction. They will form this salt and water. Now we now need to just balance the what? The number of atoms. There are two hydrogen atoms this side, two hydrogen atoms, four oxygen atoms, and then we've got four oxygen atoms, one carbon atom, and then we've got one sodium atom, one sodium atom. So that would actually but however, we can see that this is H plus and this one is Na plus. So here we have to have 2 because carbonate is actually a CO3 2 minus. Whilst when it reacts with an Na plus, it will form what? Na2CO3. So if I'm now having 2 this side, I also need to have 2 that side. So I would say here I'm having 2, here to be 2. So and now you have got what? 4 oxygen atoms and then 4 hydrogen atoms. So I would come and multiply by 2 this side. So that would be a balanced reaction between what? Carbonic acid and what? Sodium hydroxide. So this is a acid-base reaction which we call neutralization. So we form a salt and water. We form a salt and water. Now they are now saying 2 grams of sodium hydroxide, 2 grams of sodium hydroxide is dissolved in water to make 100 what? Cubic centimeters solution. Calculate the concentration of what? Concentration is just number of moles divided by volume. So how do I find the number of moles of sodium hydroxide? I will simply say number of moles of sodium hydroxide. It will be mass over molar mass. That is 2 grams all over, say 24 plus, this is actually what? 23 plus 16 plus 1, that is divided by 40. So if you say 2 divided by 40, that would actually get to be what? If you say 2 divided by 40, 2 divided by 40, that will give you 0.05. So the number of moles there will just going to be 0.05 moles. So I'll take 0.05 moles divided by the volume. If I say 100 cubic centimeters divided by 1000 cubic centimeters, I would form 0.1 decimeter cubed. So these are the values. I'll take 0.1 decimeter cubed. The concentration there was just going to be equal to 0.5 moles per decimeter cubed. Now they're saying calculate the pH of sodium hydroxide. Calculate the pH of sodium hydroxide. This dissociates to form Na plus plus OH minus. And the same concentration that I have here would be the same concentration that I will have on the OH minus ions. So for me to calculate, let me say that for me to calculate the pH there, I would simply use the concentration of what? Of OH. So I would say that, let me just get to take it this side. So I'm saying that sodium hydroxide dissociates to form sodium and OH minus ions. So the concentration here would be equal to the concentration here. So I would say concentration of what? OH minus ions is actually equal to what? 0.5 moles per decimeter cube. If that is the case, I know that pH, which is equal to 14, it is given by the what? By the P of H plus the P of OH, where I'm saying that I'm actually looking for what? For this pH. So I would say this is going to be equal to 14 minus P of OH. That is going to give me pH. How do I calculate P of OH? P of OH, I would simply say that negative logarithm of the concentration of what? Of OH minus ions. What? That is negative logarithm of 0.5. That will give me what? If I say negative logarithm of 0.45, 0.5, sorry, it will give me 0.30. So I'll now get to say that my pH from this equation, my pH would simply be equal to what? It will simply be equal to 14 minus 0.30. That is equal to what? That is equal to 13.69. So that is equal to 13.69. That is how you calculate the what? The pH of a compound. That is how you can calculate the pH of a compound. So sodium hydroxide is a strong base, so it completely dissociates in water. When it completely dissociates in water, it gives us what? Sodium ions and hydrogen ions. And we can use those to calculate the what? The pH. Now they're saying 5 grams of impure magnesium carbonate is added to 9.033 times 10 to the power 24 molecules of hydrochloric acid. The balanced equation for the reaction that takes place is given below. That is the reaction. Now they're saying the reaction is allowed to proceed until all the pure magnesium carbonate completely reacts. The excess hydrochloric acid is neutralized by adding 55 cubic centimeters of sodium hydroxide solution of concentration that the balanced equation is given below. That becomes the balanced equation. Now they're saying calculate the initial number of moles of hydrochloric acid. The initial number of moles of hydrochloric acid Given that these are the molecules of hydrochloric acid, I can actually get to say N is equals to number of particles. Let me say N is equals to number of particles of the compound over the Avogadro's number. That will give you what? That will give you 9.033 times 10 to the power 22 divided by 6.022 times 10 to the power 23. This was going to give you, if you divide there, that was going to give you what? It was going to give you 0.15 moles. So that was the initial number of moles of HCl. Now they are saying calculate the percentage purity of magnesium carbonate. Calculate the percentage purity of magnesium carbonate. Given that the initial number of moles of what? Of hydrochloric acid were equal to 0.15 moles. And then we have got 5 grams of impure what? Magnesium carbonate. So we are saying that we have got impure magnesium carbonate. And within this impure magnesium carbonate, we know that they say that the reaction is allowed to proceed until all the pure magnesium carbonate. So the pure magnesium carbonate is the one that reacts with what? With HCl in a reaction where we say 1 mole is to 2 to form what? Magnesium chloride. And they are telling us that the excess hydrochloric acid is neutralized by adding 55 cubic centimeters of sodium hydroxide in this reaction now. So what we can actually say is out of, so the initial NHCl initial, we said they're equal to 0.15 moles. And then out of this initial, some would be left because magnesium carbonate becomes our limiting reagent there. So we need to know the amount of HCl that reacted with what? With sodium hydroxide. So you would come and say 7.32. The first step is to calculate the number of moles of HCl that reacted with what? With sodium hydroxide. Now, how will I know those? I have been given the volume of what? Of sodium hydroxide and the concentration. So I can first calculate the number of moles of what? Of sodium hydroxide. So I know that due to 1:1, 1 mole of HCl reacting with 1 mole of sodium hydroxide, these would be equal to the number of moles of what? Of sodium hydroxide. So once I calculate the number of moles of sodium hydroxide, I would know the number of moles of hydrochloric acid that reacted with what? With sodium hydroxide under the neutralization reaction. So here I would say from concentration being equal to N over V, my number of moles can be concentration times volume. So the concentration here is 0.8 moles per decimeter cubed times the volume there, it's 55 divided by 1000. So if I multiply those two, I should get what? If I multiply those two, I would say 0.8 times, that would be 0.055. I would get 0.044, 0.044 moles. So these are the number of moles of what? These are the number of moles of HCl that were in what? In excess. If these are the number of moles of HCl that were in excess, then I can know the number of HCl moles that were what? That reacted. So here I would say number of HCl that reacted with magnesium carbonate would be equal to the initial NHCl initial minus NHCl excess. That would be equal to 0.15 minus 0.044. And that will give me what? What would be the difference there? It will be 0.106 moles. So these are the number of moles of what? These are the number of moles of HCl that reacted with what? With magnesium carbonate, with pure magnesium carbonate. So by knowing those number of moles, we can now know the number of moles of pure magnesium carbonate that reacted here. By knowing the number of moles of pure magnesium carbonate that reacted, we can now later know the what? The impure, because here they said percentage purity. So we can now later calculate the mass of pure what? Magnesium carbonate and divide it by the impure and multiply by 100. So now the reaction of magnesium carbonate is 1s to 2. So the number of moles of hydrochloric acid that reacted, we know that the number of moles of HCl that reacted, we say that they are equal to what? 0.106. So these are twice the number of moles of what? Of pure magnesium carbonate that reacted. So this would be divided by 2. So we can come back here and say, let's continue down here. We can actually come and say the number of moles of magnesium carbonate that reacted, the number of moles of pure magnesium carbonate, this would be for pure magnesium carbonate, are equal to half of the HCl that reacted, divided by 2. That is 0.106 divided by 2. That is going to give you what? If you divide by 2, you are going to get 0.053 moles. Now, to calculate the mass of pure magnesium carbonate, we're just going to say number of moles times its what? Its molar mass. So the molar mass of pure magnesium carbonate was going to be equal to what? What is the molar mass of magnesium carbonate? So this is equal to 84. So we can say 0.053 times 84. We can say 0.0 times 84. This would be equal to 4.452. This should be 4.452 grams. So we now know that the pure magnesium carbonate mass was equal to 4.452 grams. Out of 5 grams of what? Impure magnesium carbonate. What becomes the percentage purity? Now the percentage purity actually becomes this pure mass divided by impure times 100. So purity, percentage purity, you would come and say percentage purity of what? Of magnesium carbonate would be equal to what? Mass of pure magnesium carbonate divided by what? By the impure mass. Divide by the impure mass times 100, or else by the total mass. You divide by the total mass. So here we can actually come and say 4.452 divided by 5 times 100. That becomes to say 4.452 divided by 5 times 100. That was going to give you 89.04%. You were supposed to get 89.04%. That is the percentage purity of what? Of magnesium carbonate. That is how you were going to get the what? The percentage purity of magnesium carbonate. So that was that for question number 7. Now let's go to question number 8. Let's go to question number 8. So you will see that question number 8 is now saying a solution of nickel 2 nitrate is placed in a zinc container. It was observed after some time that a chemical reaction has taken place. The net ionic equation is zinc plus that nickel to form. And then now they're saying explain the term redox reaction. So redox reaction, we know that a redox reaction is a reaction that involves electron transfer, or else it is a chemical reaction that involves change in oxidation state. As long as there is change in oxidation state, then there is what? It is a reaction that involves change in oxidation state of what? Oxidation state of compounds. Or else it is a reaction that involves both oxidation and what? And reduction. An oxidation and reduction reaction. That is why we call it redox, to say reduction plus oxidation reaction. So you can either get to say it is an oxidation reduction reaction, or else it is a reaction that involves change in oxidation state of what? Of compounds. Now they're saying which one of zinc or nickel 2 plus is the oxidizing agent? The oxidation agent is the one that is its oxidation number or oxidation state being what? Being reduced. So you can see that nickel 2 plus is going to become nickel. That is actually what? Having what? An oxidation state of 0. So this is the one that has been reduced. So as it is reduced, it is actually oxidizing. So Ni2 plus becomes your what? Your oxidizing agent. So an oxidizing agent is an agent that is reduced in preference of the other being oxidized. Explain the answer by referring to the oxidation state. So you will say that nickel 2 plus is having its oxidation state being reduced from 2 plus to 0. So we have got a reduction in the oxidation state of nickel 2 plus from 2 plus to 0. Maybe that is what I was supposed to say there. Let me just get to use a bigger space and explain it in that way so that it becomes easier. So you just come here and say nickel 2 plus, why? The oxidation, its oxidation state is being reduced from 2 plus to 0. Its oxidation state is being reduced from 2 plus to 0. That is what you're supposed to say there. Now they are saying explain the answer referring to the oxidation state. That is what we have just done. Give a reason why the nitrate NO3 minus is not written in the net ionic equation. Because it is a spectator ion. It is a spectator ion. What do we mean by a spectator ion? It is an ion, it is a spectator ion. It does not take part in the what? In the overall what? Oxidation reaction. It does not take part in the redox reaction. Like itself, its state does not change. Its state does not change. So it watches whilst others, they are changing from positive to a negative, or else from positive to 0, or else from negative to positive. Its own state, it does not change. So it becomes a spectator ion. It's like it is just watching football. That's why we call it a spectator ion. It is just watching whilst others are changing in their what? In their oxidation state. So that's the reason why we will not involve it in the what? In the net ionic equation, which is the overall ionic equation. Now they are saying the reaction between dichromate, which is that one, and tin in an acidic medium is given below. That is the reaction. Determine the oxidation number of chromium in what? In dichromate ions. So we can see that the overall oxidation state is what? It's a -2, where we know that this is 2 times the oxidation state of chromium plus 7 times the oxidation state of oxygen. And we know that oxygen has got an oxidation state of -2. So I would have 2 times x and then a -14. If I take that -14 this side, it would actually be what? -2 plus 14 being equal to 2x. Because here I'll be having what? -14 plus 14. These, they will cancel out to 0. So I'll be left with x is equals to what? Negative, it will be positive 12 divided by 2. So x is equals to 6, positive 6. So the oxidation state of chromium here, it's what? It's positive 6. So you just substitute, maybe you substitute X for chromium, and then you substitute the normal oxidation state for oxygen when it is reacting with what? With metals. We know that it becomes what? -2. And then you equate to the overall what? Oxidation state of the compound. And then you solve for the unknown, which is x. That becomes positive 2. Write down the reduction half reaction here. So what is being reduced? You see that chromium is coming from positive 6 to what? To just positive 3. So this is the reduction reaction. So we need to go to our what? To our standard to our table of standard reduction and get the half reduction reaction of chromium from this to that. So I have here the standard tables so that we can be able to use those. So you can see that chromium coming from here to there, its half reaction would be this one. That is what we were just supposed to copy there. So you were just going to copy that reaction. So by copying that reaction, we're going to take what? Cr2O7 2 minus plus 14H plus 6 electrons, forming what? It was forming 2 chromium 3 plus and then plus 7H2O. So we're just going to take that equation. That becomes our what? Our half equation. That is what we're just supposed to take there. So now let's see what the next question is saying. The next question is now saying pardon me there. I don't know what's now happening with my pointer. Okay, wonderful. Now we now want to look into the what? So the half reaction, the half reduction reaction, you were just going to take for what? For chromium, which was just going to be chromium 2O7 2 minus reacting with what? 14 H plus how many? 6 electrons to form 2 Cr 3 plus 7 of our what? That is what we're just going to take there. That becomes for what? For our half reaction there. Now they say use the standard reduction potentials and write down the balanced net ionic equation. Now since you now have got the what? Since you now have got the half reduction equation, you would now need the half oxidation reaction and then you combine them. So this being the half, you would have just came, let me just get to say 8.23. You would have copied this one, you would keep it because that is for what? That is the half reduction reaction, half reduction reaction. We now need the what? The oxidation reaction. And then we compare those two and then we combine them. So we can see that what is being oxidized become what? What is being oxidized in this reaction, we can all tell that what is being oxidized here, it's our tin, because our tin is coming from a positive 2 to a what? To a positive 4. So that is what we want to go and look for when it comes to what? To our standard reduction potentials. So maybe I was supposed to be looking for what? For tin here. So when you see tin, yes, there is our tin. And we can actually see that our tin, here it's coming from 4 to 2, but we want it to come from 2 to what? To 4. So we're going to take it going that side. So it was going to be tin 2 plus, and then going to form what? Going to form tin 4 plus 2 electrons. So that was the half oxidation reaction that we were going to take there. Now let's go back and write that reaction. So that being the case, I was going to say tin, just supposed to have what? Tin of, I have got tin 2 plus, tin 2 plus, uh, forming tin 4 plus 2 electrons. Now, what is left is to see that I have nothing in common here and there, but only the number of electrons. So I need to balance this number of electrons. We need to have the same number of electrons so that we can be able to combine these two. So here I've got 2 electrons, here I've got 6 electrons. So here we are losing 2 electrons, while here we are gaining 6. So I need to multiply by 3 so that they become 6 electrons that we are losing, so that they can be gained that side. When I do that, here I would be having 3, here I would be having 3, and then here I would end up having what? 6 electrons. Then I can be able to combine these two. So I was going to come and say Cr2O7 2 minus plus 14H plus, and then I add this, which becomes 3 tin 2 plus. I remove the number of electrons that are being lost because they are the same that are being gained that side. And then I'll be left with what? 2Cr 3 plus 7H. So here I could actually start with this, so that it becomes 3SN4 plus, and then I would have 7 water there. So that is what you were just expected to do there. That is what they expected you to do. So that was our question paper. Thank you so much, guys, for being together and revising using this question paper. So until we meet once again in the next coming videos, let's keep on practicing, let's keep on reading, and actually preparing for our November exams. So from us, Maths Zone African Motives, we just get to say more light, keep on shining, guys. Thank you.